Okay, so this is the second part of applications of composite functions. We're just going to do this problem right here. It should only take a few minutes. So let's get right into it. Starting at 50 meters, the radius r of a circular oil spill increases at the constant rate of 0.5 meters per second. Okay, and so the first part here is asking to express the radius r in terms of time. And remember, we talked about in terms of blank, just means the blank is going to be our input, our independent variable, our x value, any of the above. So we're writing an r of t equation. And just like the last problem, we have an initial value, which is 50, and then 0.5 meters per second. So we represent that as 0.5 t. And then add that initial value. And so that will be the radius over time. Part B says, if the area of the circle equals pi r squared, find the composite A of r of t and explain its meaning. So it looks like they already gave us the relationship between A and r. A is going to equal pi r squared, which we knew, but it was given to us. And we want to find A of r of t. Remember, we can also write it this way. We just found r of t, it's in part A. And basically what that means is everywhere we see r, we're plugging in r of t, and I'm just going to keep repeating that because repetition will help it stick. So A of r of t is going to equal pi, and then I see an r, so I'm going to put my function in there. 0.5 t plus 50 squared. Cool. All right. And so now we see that we related area and time when in the beginning we had a relationship between radius and time and between area and radius. So we just made the connection between area and time. And then explaining its meaning, that's kind of the same thing we did in the last problem. So basically this function is giving us the area of the oil spill over a number of seconds. So, and you can include units in that explanation. You could say, what would it be? The area of the oil spill in meters squared over t seconds. That's one way you could write that. And here. So I would just write it the way that it looks in part C. I'm not going to do it right now, but so just like this, you're giving the dependent variable, so height, area, whatever, area of what, height of what, and then what does it relate to? Time, cost, whatever the situation is. Okay, and the reason I chose this problem is for part C, so we're going to focus on that. It is asking how long will it take the area to be larger than 10,000 meters squared. So this is where it's important to do compositions, is if you need that relationship between area and time, because you're trying to figure out, when is the oil spill going to be this size? And area is always a lot more useful than radius, so it would make sense for us to do that operation. So we see the phrase larger than, which means we're going to have an inequality. So when is the area going to be larger than 10,000? And then we just plug in our formula and do normal algebraic things on both sides until we isolate t to be larger than 10,000. I forgot to square it up here. Okay, so you would end up right here. This is squared. the answer key did this as well. So that's probably why I had that in my mind. So this is actually squared. We would do the square root of both sides. Very important. And then so you would do that. I'm just going to leave it in that form because I don't want to calculate it right now. Greater than square root of 3185. I'm going to move this along. You would subtract 50. Okay, and then after you do that, you would divide both sides by 0.5. And that would cancel out. So then you would be left with t is greater than, and then when you calculate all of that on the right, you're going to get approximately 30 seconds. Cool. All right, well, that's it for this part. So I hope you join me for some domain stuff in the next video.